This lesson is 2.3.1 and focuses on materials properties. The big concept of this lesson is that you will learn about material properties and the questions engineers must ask when selecting appropriate materials. First, let's look at the role of materials. During the reverse engineering of your consumer product, you were asked to identify the materials used in its design. You might have picked up on a part of the product and, through observation, deduced that it was metal or plastic. What characteristics led you to this conclusion? Why did the product designers decide to make the part using that specific material? Does the selected material support the visual, functional, and structural requirements of the product? Consider that everything must be made from something. Materials can loosely be defined as the stuff we use to make things. A more precise definition of a material includes the qualities that give something its individuality and by which it can be categorized. How a material performs in a specific application depends on its properties, its response to heat, light, and other stimuli, and the structure of the material, beginning with the atoms the material is made of. So how are materials structured? In materials science and engineering, structure refers to how the atoms, or molecules, are arranged in a material. A solid material exhibits either a crystalline or amorphous arrangement of atoms or molecules. A crystalline solid has an atomic structure characterized by a regular, repeating, three-dimensional array of atoms, ions, or molecules. Examples of crystalline materials include ice, salt, quartz, diamonds, zinc, and iron. An amorphous solid has an atomic structure characterized by a more or less random, three-dimensional arrangement of atoms, ions, or molecules. Examples of amorphous solids include glass, gels, wax, and some plastics. On the left in that image, you'll see what a crystalline structure looks like. The image on the right is of an amorphous solid. So let's take a look at structure and properties. Now let's take a look at structure and properties. So the structure of a material directly relates to its properties, which in turn determine its performance. Structure is affected by how a material was made and processed. That can include things like machining, molding, bending, rolling, welding, or heat treating. However, a material's structure can also affect how it can be processed. The graphical model on the next slide illustrates these dependencies. Engineers need to be aware of these interrelationships when choosing materials and specifying manufacturing processes. For example, metals conduct electricity. Another property of metals, ductility, allows it to be processed into a wire. Applying a heat treatment process, such as annealing, changes the crystal structure of the metal wire. This process improves the performance of the wire by increasing the electrical conductivity of the metal. So this graphic represents the codependencies of a material. You'll notice at the top that we have performance, and performance relies upon processing, properties, and structure. Depending on how a material is processed, how it is structured, and the properties of the material determine how the material will perform. So, how will we go about identifying different material properties? Well, there are 6 total material properties that we will be discussing. This includes mechanical properties, electrical properties, thermal properties, optical properties, magnetic properties, and chemical properties. Mechanical properties are the response of a material to an externally applied force. The many mechanical properties include strength, tensile strength, hardness, stiffness, and ductility. The questions that we have to ask when analyzing a mechanical property include: does the material deform when it is pulled or compressed? Does the material break when impacted? And can the material flex and return to its original shape? Next, let's take a look at electrical properties. Electrical properties are the response of a material in the presence of an electric field. Electrical conductivity and resistivity are electrical properties of a material. When analyzing the electrical properties of a material, we have to ask if the material is an electrical conductor or insulator. Now let's take a glance at thermal properties. Thermal properties are the response of a material to externally applied heat. Thermal properties include the capacity to maintain heat, thermal conductivity, thermal expansion, and melting or boiling points. When we analyze the thermal properties of a material, we ask, does the material expand as it heats up? Is the material a thermal conductor or is it an insulator? Can the material tolerate a rapid change in temperature? Or will the material soften during processing? Next, let's take a look at optical properties. Optical properties define the response of a material to an externally applied light source. Optical properties include color, absorbability, transmittance, reflectivity, and fluorescence. When we analyze materials for optical properties, we have to ask, does the material absorb or reflect light? And is the material transparent, translucent, or opaque? Then we have magnetic properties. Magnetic properties define the response of a material to an externally applied magnetic field. And we have to ask ourselves, is the material attracted or repelled by a magnet? Then we have chemical properties. Chemical properties quantify how reactive the material is to an externally applied chemical agent. This includes how the material's other properties might degrade over time, such as whether a material will corrode in air or water. Chemical properties include reactivity, combustibility, surface energy, pH, and corrosion resistance. If we're analyzing the chemical properties of a material, we have to ask ourselves, does the material corrode in air or water, and how quickly does it corrode? And then, does the material react to an acid, such as vinegar? So how do we choose a material? Product designers must consider both the physical properties of the object they are designing and the material properties of the materials they propose when designing a product. A product's size, shape, volume, and weight impact its visual, functional, and structural characteristics, as well as the cost of raw materials in manufacturing. However, the physical properties of the product alone do not determine the success of the product. The materials from which the product is made also impact the visual, functional, and structural characteristics of the product and cost. Because performance is linked to a material's properties, it's important for engineers to have a basic understanding of how a material's properties can impact its performance. In designing a product, designers have a purpose, such as to make the product as inexpensive as possible or as safe as possible. These objectives are subject to constraints. The cost must be below a certain limit, the product must withstand a certain load without failure, or the weight of the product must be below a given value. When selecting materials for a product, a designer must consider all aspects of the design, and trade-offs are often necessary to achieve design criteria and constraints.